session, we started off with introduction to dynamic programming, and in today's session, we'll just continue with it and learn some more advanced concepts in dynamic programming. Today's session will be conducted by Charan and Jigyasa. Yeah, so Charan, you can start.
Yeah, hello everyone. Is my cam? Am I audible?
Yeah, you're not. And
Yeah.
visible also.
Yeah. So good evening, everyone. I'm Charan, programming club coordinator. Today I'll be discussing some advanced DP algorithms and with some example standard DP algorithms, standard DP problems, longest increasing subsequence, and LCS. So let me share the screen. Is my screen visible?
Yeah, it's visible.
Okay. So yeah, once again, welcome to WPC session 2. So yeah, without any delay, we'll go to the first problem. So the first problem is longest increasing subsequence. So as the name suggests, our first task is to find, given an array of numbers, our task is to find the longest increasing subsequence, the length of the longest increasing subsequence. So for example, consider this array 6, 2, 5, 1, 7, 4, 8, 3. A subsequence is defined is something you get from an array by removing some of the elements and without changing the order of the remaining elements. So 2, 5, 7, 8 for this array is a subsequence, whereas 2, 5, 8, 7 is not a subsequence because we changed the order of 7 and 8. So our task is to find the length of the longest increasing subsequence. Increasing in the sense, it's increasing from left to right. So in this example of all possible subsequences possible for this array, 2, 5, 7, 8 is a subsequence with the longest length, with the highest length. The length is 4. So any ideas? Of course, not brute force. Like we can find every possible subsequence, and find the highest length. Not that. Any other ideas on like how to approach this problem? By the way, is the question clear? First of all. Anyone in the attendees? Anyone? Okay, I take that as yeah. So before finding a solution, as we know, this is a DP question. So before writing any DP solution for any problem, we need to have 3 things ready with us. Its first one is state. The state of a DP is what DP of I represents. It may represent directly the length of LCS till it may represent length of LS till ith index or anything. We need to know what DP of I represents. Then we need to have transition on transition is how do you find DP of I with the values you already know. The values can be anything from DP of 0 to DP of I minus 1, anything. With already previously calculated values, how do you find the value of DP of I? What is the logic? This is the logic part. And then base case. The base case is if you want to initialize the DP array with some value already. What is it? Like if we want to initialize the array, every element in the array to 1 or 0, what is the base case? This is like the trivial case. We need to take care of these base cases. So for LIS problem, we'll start discussing about the state. Let's say DP of I represents length of longest increasing subsequence in the array considered from 0 to ith index, 0 to ith index, and containing ith term. We'll look at this with an example. Consider the array 6, 2, 5, 1, 7, 4, 8, 3, 6, 2, 5, 1, 7, 4, 8, 3. Here dp of 0 is length of the longest increasing subsequence from 0th index to 0th index containing this term. So it is just 6. So the length is 1. Let's see what is dp of 1. So dp of I must definitely contain the ith term. So we're definitely going to have 2. But we don't have any term which is less than 2 from 0 to first index. So we don't have any. So dp of 1 is also 1. Look at dp of 2. From 0 to second index and containing second term. I mean second indexed term, which is 5. So we have one term less than 5 from 0 to second index, which is 2. So dp of 2 is 2. Look at dp of 3. We should definitely have the third indexed term, which is 1. And we don't have any numbers less than 1 from 0 to third index. So we don't have any. So dp of 3 is 1, and so on. So let's say we know every value from dp of 0 till dp of I minus 1. How do I calculate dp of I? Anyone? Any logic? Look, how can I apply? By the way, is the state part clear? Like if you have any doubts, you can ask. Okay. So I'll continue with the transition. Now I'm finding transition. Transition. Oh, okay. Yeah. So I'll start transition again then. Okay. So yeah, starting with transition, let's suppose our array, our given array is A. So we have elements A of 0, A of 1, and so on till A of n minus 1. N is the size of the array. But while calculating dp of I, we only care about the first I plus 1 terms. So basically till I A of I. So we'll take only till A of I. So while calculating dp of I, let's suppose there is some element A of j in between A of 0 to A of I, that is j less than I such that a of j is less than a of I. Then whatever the increasing subsequence we have till a of j, that is represented by dp of j, we can add one more element a of I while calculating dp of I, so that we have a new increasing subsequence of length dp of j plus 1. So to find the maximum value of longest increasing subsequence of all these possible subsequences, we need to find the maximum of all dp of j plus 1 such that j less than I and a of j is less than a of I. Is the transition fine? Okay. Now we look at the base case. Let's say there is no a of j such that a of j is less than a of I from a of 0 to a of I. Let's say there is no j such that a of j is less than a of I. Then what is the value of dp of I? Is 1, which is like the set of a of I itself. So this is the base case. So we initialize all dp values to 1. I'll show you the code, and then for the transition, this is for the transition part. For I is equal to 0 to array dot size, I initialize length of I is equal to 1. Here, by the way, here length is the dp array. So length of I is equal to 1, which is the base case here. dp of all possible values is equal to 1. And from j is equal to 0 to I, we are checking if a of j is less than a of I. If a of j is less than a of I, we'll update length of I is equal to maximum of length of I comma length of j plus 1, so that by the end of the loop we'll get only the maximum value, and what we'll be getting is the length of the longest increasing subsequence considered from 0 to I, with ith index term as the last term. So this is the transition. Time complexity for this is n square, since as you can see, this the time complexity is n square. I initialize dp of I is equal to 1 and check every value from 0 to I, and then again I put dp of I plus 1 is equal to 1 and check from 0 to I plus 1. So this is basically n square algorithm. As you can see, this the time complexity is of n square. So I'll code this now. We take the value of n first and input the values of the array, and then we initialize our dp array, dp of n, and fill all these values with 1. So what this line does is it initializes every value of dp of 0 to dp of n minus 1 to 1. So initialize this is the base case. Yeah, this. Yeah, for I is equal to 1 to n and j is equal to 0 to I, we are checking if a of I is greater than a of j. And if it is greater than a of j, we are updating the value of dp of I only if it is greater than the previous value we had, so that we only get the maximum value at the end of the loop. And let's say ans is our final answer. For int I is equal to 0 to n, this is just finding the maximum value of all possible values of dp of I. So observe that, yeah, this is the main point. Our final answer is maximum value of our array dp. So our longest increasing subsequence might end with any of the n terms. So dp of I represents the longest increasing subsequence with ith term as the last term, right? So we need to find the maximum value of all the possible dp values. So as our longest increasing subsequence might end with any of the terms. This is the final code. This is the same. And as you can see, we can clearly have an optimization here. In this example, when I'm calculating dp of 4, let's say, we have 7 for sure. And when I consider, if I take 5 less than 7, I consider this subset here. Also, I consider 2, 5, 7, 2, 7. Also 2, 5, 7. Oh, not this. While iterating from 0 to 4, 0 to 3, we check if 2 is less than 7 and add 1 to the LIS of 2. Also, we check that with 5 also, but there is no need to check with 2, 7 because we already know it's already there in 2, 5, 7. So there are clearly optimizations possible, and I will not be discussing any optimizations in this session. There's actually a DP greedy solution also for this using a concept called patient sorting. And using this patient sorting, there's another DP solution of time complexity of n log n. Yeah, any doubts in LIS? Okay, if there are no doubts, we'll move on to the next problem, LCS. LCS, as the name suggests, we need to find, given two strings, we need to find the longest common subsequence of the given two strings. So again, subsequence is a sequence you can obtain from the string by removing some elements, like possibly 0, but without changing the order of the remaining elements. So B, D, E is a subsequence of A, B, C, D, E, F. And similarly, B, D is also a subsequence of B, F, D, U, X, E. Now, we need to find the common subsequence. We need to find the length of the longest common subsequence, which is like common to both the strings. So Any ideas on how to proceed? Okay. Here, the length of longest common subsequence is 3, and the common subsequence is B, D, E in the same order. So again, we'll start with state, transition, and base case. It says state. Yeah, before discussing the DP solution, first we'll see a recursive solution for this problem. Let's say LCS of x, y, and m gives you the lengths of LCS of strings x comma y, and x comma y have lengths n comma m. Okay, so x LCS of x, y, and m returns the length of the LCS of strings x comma y. So let's say we have the strings x, y, x is of size n. So we have x of 0, x of 2, and so on till x of n minus 1. Similarly, y of 0 to y of m minus 1. So looking at the last characters of these two strings, we have two possible cases. The last two characters are either equal or they are not equal. In the first case, suppose they are equal. Okay. Suppose they are equal. Then LCS of x comma y is just 1 plus LCS of x comma y without the last two, like without the last character. So we consider till n minus 1, such that the length is only n minus 1 and m minus 1. And if they are not equal, we have two cases possible. So LCS of x comma y can either be LCS of x, y, n comma m minus 1, or LCS of x comma y comma n minus 1 comma m. This is because since the last two terms or last two characters are not equal, as these two are not equal, even if we remove this term, this character from the string and find LCS of these two, and or that does not affect it. So we are basically reducing to a smaller problem, and LCS of x comma y comma n minus 1 comma m. So we remove this term, this character, and find LCS of these two, and we remove this character and find LCS of the remaining remaining two strings. The LCS of final x comma y will be maximum of these two, because if this last character, let's say this last character is there in the final answer of, or is there in the final LCS, then it will be there in this LCS. So LCS of x, y, n comma m minus 1. If this term is there in LCS, this term cannot be there because this is the last term, and this term is not equal to this term, so that cannot be there. This term cannot be there in the LCS if this term is there. Similarly, otherwise, so we can just remove this last terms and find the LCS. Since LCS is the maximum value of these two, we find maximum of LCS of x, y, n, comma, m minus 1, LCS of x, y, n minus 1, comma, m. Yeah, so this is the recursive solution. The time complexity will be 2 power n, where the worst case is when there is no common subsequence on both the strings. So let's say we have strings A, B, C, and D, E, F. We'll start from the end of the both strings since C is not equal to F. The LCS of these two will be either LCS of this or this. Similarly, since these two are not equal, you can divide this again and then again. So the total time complexity will be 2 power n. Next, DP solution. Okay. Let's continue this graph so that we have a better observation on why we need a DP solution. A, B, D, E, or A, comma, D, E, F. Here also A, B, comma, D, E, or A, B, C, comma, D. In a recursive solution, we will be finding the LCS of AB comma DE twice. So this is same as when you find Fibonacci in Fibonacci sequences. When you have the repeated terms, we just memorize them. So what we'll be doing is memorization for this problem. So again, for DP solution, we need to start with the state. This time we'll take a 2D DP. DP of IJ represents LCS of strings x comma y, where x is considered from 0, the string in x is considered from 0 to x of I. I minus 1, and I terms from the first string and j terms from the second string, and dp of ij returns the LCS of first I terms in x and first j terms in y. So this is the state of the DP transition. So if x of I minus 1 is equal to y of j minus 1, same logic as in recursive solution. If x of y minus 1 is equal to y of j minus 1, equal to then LCS is 1 LCS of x comma y comma I comma j also is there. Is same as LCS of x comma y I minus 1 comma j minus 1 plus 1. So that we can eliminate x of y minus 1 and y of j minus 1, and LCS of these the remaining string plus 1 will be the length of the uh, longest common subsequence in x comma y. Consider till I comma j, I comma j terms. So else if they are not equal, LCS of x y I j will be maximum of LCS of x comma y comma I minus 1 comma j comma LCS of x y I comma j minus 1. Next is base case. Since we are memoizing this, and this will be a top-down solution. So the only base case needed is dp of 0 comma of 0 of 0 is 0. This is like consider till 0 terms, and consider till 0 terms we don't have any common subsequences, so the length of the longest common subsequence will be 0. So we'll have a look at the code here. I take input two strings x comma y, initialize m is equal to size of string x and n is equal to size of string y, and I initialize a DP array. This is a vector of vectors, which is like similar to a 2D array, and I initialize every value to -1, so that since this is the memoization, we need to know if the value is calculated or not. So we initialize all other values to -1. So we see out LCS. Looking at the function LCS string x, string y, m, n, and we pass the array dp. If m is equal to 0 or n is equal to 0, return 0, so that if there is no element in string x or string y, we return 0. So because there is no common subsequence. If dp of m comma n, dp of m n is not equal to -1, which means we already calculated the value of dp mn, so we just return dp of mn. Else, if dp of mn is equal to -1, that means we did not calculate it earlier. So if x of m-1 is equal to y of m-1, we return dp of mn is equal to 1 plus LCS. If they are equal, we return, we decrease 1 in m comma n. It's like removing the last element. Else dp of mn is equal to maximum of LCS of x y comma m-1. We remove the last element in the first string, and second element stays the same. Second string stays the same, and vice versa. We need to find the maximum of these two, and this will be the value of dp of mn. And time complexity of this is of mn. Worst case being no common subsequence between these two strings. Any doubts in LCS or LIS? Okay, so So Jigyasa will continue with LCS bottom-up approach and matrix multiplication.
Charan, you can stop sharing your screen. Am I audible?
Yeah, you are.
Yeah. Okay, I guess there are no doubts regarding LIS and LCS talk. So we'll begin with the
I
LCS.
guess you could be a bit more audible. Like your voice is soft.
Oh, is it fine now? Is it
Yeah,
fine
I
now?
guess. Yeah.
Oh, okay. Thanks. Yeah. So, okay. Let's begin with the bottom-up approach for the LCS, that is the longest common subsequence. So before beginning, does anyone have any idea regarding what is the bottom-up approach? Wait a second, else. Okay, is my screen shared? Can anyone answer?
No, I don't think so.
Oh, just a second.
Yeah, now it's visible.
Oh, okay, fine, thanks. Okay, so before beginning, let's just see once what is bottom-up approach. So, I think the drawing board is visible, right?
Your voice is low, I guess.
Is it fine now?
No.
Okay, how now? Hello, am I audible?
Yes, you are audible, but then your voice is very low.
Is it better?
Yeah, it's better now.
Oh,
Can be bit louder.
okay, yeah, fine. I think that works, right?
Is it fine for others or is it only me?
It's clear, I guess.
Oh, okay, fine. So, okay, I'll just begin. And if you feel anything issue with the sound, just please speak up. Okay, so just let's begin with the bottom-up approach. Um, when you speak of the bottom-up approach, it's actually it means that you start from the base, you build up the solution, and then you pick up the smaller sub-problems. And with the help of those smaller sub-problems, you will build up the final solution that will be the optimal solution for your question. So when you go for a bottom-up approach, it is you start from the base case. That is, you have to start it in the iterative way, which is different from the top-down approach. That is actually the recursive way. So for starting with the iterative way, we should start with, first of all, initializing the table that we are gonna fill. So as you know, the table that we will be using will be the two-dimensional array. That will be the 2D array. Can anyone give the reason why we will be using 2D array instead of one-dimensional? Or like, is 2D sufficient or not? Anyone? Okay, so okay, the thing is that when you calculate LCS depends on both the two parameters, the length of both the strings, that is x and y. If you need to calculate the longest common subsequence of x and y.
Jigyasa, your screen is not visible, like whatever you're writing.
Oh, is it?
Yeah. I think you should share the tab. Oh,
Yeah, okay. Is it visible now?
Yeah, it's visible now.
Oh, okay. Thanks, Anna. Yeah. So for the, okay, we are saying that if you need to calculate find the LCS of X and Y, then you need to find, okay, for finding the longest common sequence of X and Y, you need the length of X and Y, that is M and N, and that's why you need a two-dimensional array. And when you want to fill the 2D array table, that is the two-dimensional array, the matrix of the 2DP, for that it started with the base case. And as the base case stated earlier, is either M is equals to 0 or N is equals to 0, because the DP will be, for that particular state, will be 0. So while filling the table, the first loop starts with filling the first row and the first column of the table will be 0, as which implies that either the length of the X is 0, either the string X is null or the substring Y is null. So we start with filling the first and the first column to be 0. And to go on with the iterative solution, now we need to fill the rest of the table. We need to develop a relation between the states so that you can fill the rest of the table. And the relation, the state here is dp of ij. So does anyone want to guess what will be the relation? What will be the dp of ij? Okay, fine. Actually, the one that has been already told. dp of, when you say the ij or when you say whatever LCS, you just have to check either if your x of I minus 1 is equals to y of j minus 1, then it will be 1 plus dp of I minus 1 j minus 1. Else, if the x of I minus 1 is not equals to y of j minus 1, the dp of ij will be max of dp of ij minus 1 or dp of I minus 1j. Is that clear? Any doubts? So, okay, can everyone see the slides that I'm sharing? Is it visible?
Not the slides, the Z board is visible.
Oh, I guess it's visible now, right?
Yeah, it's visible now.
Oh, so, well, let's see. So, when you are saying for the bottom-up approach, the first of all aim was to create the solution of the smaller problems in an iterative way so that you can store the result in the table. So, how to build up the thing is, first of all, you need to think of the table structure. So as we know that you are finding the longest common subsequence of two strings X and Y. So your table structure will be a two-dimensional array because it depends on both the parameters M and N. Then when you need to determine what will be the table size will be M plus 1 into N plus 1 instead of Mn, because here we are considering the case where either of the strings could be null. We have to also consider the case where either X or Y can be the null string. So this will be the thing. The another goes for the table initialization. Here you need to initialize the table because we know the base case is if either of the strings could be 0. So in that case, the first row and the first column of the table will be filled with 0. And when you go, what will the structure you will need to require to fill the table will be the iterative thing. For that, LCS of ij, as that is the only recursion we have used, you can just fill that LCS of ij will be 1 plus LCS of I minus 1 j minus 1. If the last thing that you are seeing in the string is equal, if the characters in both the string are equal, if they are not equal, then it will be the max of I j minus 1 or I minus 1 j. The better picturization we can view in this, where here the yellow box determines the LCS of ij, and here we have the condition that the last string, the I minus 1 and the j minus 1 index that you are viewing are not equal. In that case, you have to find the maximum of LCS of I j minus 1 and I minus 1 j. In the same case here, when the x of I minus 1 and y of j minus 1 are equal, if the last characters of the both the strings are equal, then it will just be 1 added to the LCS of I minus 1 j minus 1. And yeah, the iterative code will begin with initializing a array, 2D array, and then you are initializing the first row and the first column to be 0, and then you are using the iterative structure to fill the table. And of course, the result will be stored in the LCS of m comma n. You will return that and you'll get the answer. So just let's go through the example how it will be filled. Let's say the two strings that you have been viewing will be, one is CBDA and another is ACADB. So as the first, it begins with filling the first row and first column to be 0. The first and first column will be filled. The second will be with, let's say the second row and the second column. Here you see A and C. So you know both are not equal. So you will just see the maximum of its adjacent rows and the adjacent above row and the left row. Here both the maximum of both of them is 0. So here the 0 will come. The same case, let's come to the second row and the last column. Here A and A are same. It means that when you have CBDA and only A as a string, the maximum or the longest common subsequence that you're going to get is A. So here you will get the 1. So it is just actually 0 when you get any two characters equal, like A and A are equal here, then you will just add 1 to its diagonal element. So here it was 0, it's the 1 is added. The same case, let's come here, where in the fourth row, the last column, here again A and A are equal. And so if A and A are equal, it means you have to see its diagonal element and just the 1 added to it. And this is how you get 2. And so on it goes on. And if you don't find them to be the equal, then you will just say, let's say for the second last row, the last column. Here, when you want to fill the 2, the D and A are not equal. So you just take the maximum of the side, the previous row and the above row. The maximum of 2 and 2 is 2, so here the 2 is given. So at last, this 2 will be the longest common subsequence of both these strings. Okay, so as you know, the time complexity will be polynomial order mn, and the space complexity will also be order mn. What do you guys think? Can it be optimized further? Any idea? Okay, let's give the hint. It can be optimized with the space complexity. Like the space complexity can be optimized further. Anyone? Okay, it's fine. Let's see. So actually, if you see one thing here in this image, you know, when you need to calculate the longest common subsequence of ij, you just need only the two values, the first row, the row in which it is present, and the above row. Actually, there is no need of storing all those them, because for calculating I and j, you just need these above two. And secondly, you are filling it in row-wise fashion. Row-wise fashion in the sense you are filling from left to right. So it means that you, instead of taking all, you can just maintain it into a 2D array of 2 rows, and the rest will be the column of the other thing. So yeah. The thing is that you have only adjacent indices in the table are used to build the solution. That is, for LCS of ij, you either need I minus 1, j minus 1 or ij minus 1, I minus 1, j. And when you look at the code here, whenever you fill the table, you always start work in the row-wise fashion. That is starting from the top row to the last row, moving from left to right. So in this way, because of that, instead of taking M cross N sized array, you can use only 2-row 2D array, which will reduce your space complexity from a quadratic time to a linear time. And so the same thing you can use here too. So the first time, all the rows will be initialized to be 0. The first row will be initialized to be 0, and the later you will just use this code in the way where you will be using I percentage 2 as the reason to fill it, and I minus 1 percentage 2 will get the above row, and I percentage 2 will get you the current row. The same way you can return the LCS of M percentage 2n, which will return you the answer, and the space complexity will be linear time. Okay, so does anyone have any doubt till now? Okay, so like we'll have a 2-minute short break, and after that we'll continue with the matrix chain multiplication. In the meanwhile, if anyone has any doubt, they can raise their doubt, or if any part that isn't clear. Okay, let's begin. I hope no one has any doubt. So, okay, let's then begin with the matrix chain multiplication. So, is the Zeitport visible? Is it?
Yeah, it's
Yeah, it's
visible.
visible.
And okay, and the audio is fine, right?
Yep.
Yeah. Oh, okay. Thanks. So let's begin with the matrix chain multiplication. So it starts with given, let's say you have been given four matrices, A1, A2, A3, and A4, and you need to multiply the matrices and you need to return the, okay, just let's say when you need to multiply the matrices, what there can be many ways, right? You can multiply A1, A2, A3, A4, and you can and then you can return the final solution. Or you can begin with multiplying A1, A2, multiplied with A3, and then with A4. As we know, both will return the same answer, but will both return the same cost of multiplication? Actually, no. So, what is meant by cost of multiplication of matrices? If you say you have two matrices A and B of dimension m cross n and n cross b, then AB, or the cost of multiplication of the matrix A and B, will be m cross n cross b, which implies actually the total number of the element multiplications to be performed while performing the multiplication of the matrix A and B. So, yeah, consider you have these A1, A2, A3, A4. Then you know there are total 5 possible ways in which they can be multiplied. When you talk of their cost of multiplication, the cost of multiplication will be in among these three, the minimum is the third one, which is 7,000. So it's like first you're multiplying A and B. B has the dimension 50, 20, and 21. So the first multiplying A and B will give you the cost 50 into 20 into 1. Multiplying CD will give you the cost here. The C has dimension 1 cross 10 and D has dimension 10 cross 100. So multiplying C and D will give you the cost 1 into 10 into 100. And then multiplying the result obtained from AB and CD will be the cost 50 into 1 into 100. So the total cost here will be 7,000. So the question is, actually you will be given the matrices in the form of an array. In the sense, if you will be given an array of length n, and that length n will have n minus 1 matrices. In the sense, if let's say you have a length of size, an array of size 5, so you will have 4 matrices. And if you say A, B, C, D are the 4 matrices, then dimension of A will be array of 0 into array of 1. For B, it will be array of 1 cross array of 2. It will see array of 2 cross array of 3. And D will be array of 3 cross array of 4. So in general, for a matrix, if you need to find the dimension of AI matrix, it will be array of I minus 1 cross array of I. Given this, you have to calculate the minimum cost of multiplication of these matrices. So when you begin calculating the minimum cost, the first of all, the first approach that come, or you can say the naive approach, is going through all the possible cases and then finding which will be the minimum among them. So does anyone wanna say what can be the naive approach for the, does anyone have any idea? Uh, okay, so let's say you have the matrix A, B, C, D. You need to give the minimum. So cost of multiplication of this matrix. So there are 3 ways you can split this matrix. You can split the matrix at here, or the second will be split after B, Third will be split after C. Means you multiply A with BCD. Here you're multiplying AB and CD, and you're multiplying ABC and D. This BCD can further be divided into two with one split at B and another split at C. So it will become like ABCD multiplication or ABC multiplication, and D. This won't be split at further. Here it will be A multiplied with BC multiplied with D, and or you can just say AB multiplied with C multiplied with D. So as a result, you got 5 combinations that we were saying about. This is how this works. So if you look properly, in the same way, if you want to split up it in the array, how will it work? Let's say for the ABCD, you have been given an array. And you have, if you want to split at A, B, C, D, so here the split would work at 1, because it will be 0 to 1 and 1 to 4. The same for ABCD, the split here will be 0 to 2 and 2 to 4. And for ABCD, the split will be 0 to 3 and 3 to 4. Because if you go from 0 to 1, 0 to 1 will give you the index of A, 1 to 2 will give you the index of B, 2 to 3 will give you the index of C, and 3 to 4 will give you the index of D. For splitting it, so you can say that you are multiplying the matrix A with the rest of the multiplication of B, C, D, which is shown by this matrix. And for the same A, B, and C, D, 0 to 2 and 2 to 4. I guess the split is cleared, is it? Does anyone have any doubt? You can type in the chat. Okay, maybe I guess it's clear. So let's see. Actually, you will be given the dimension of sequence of matrices in an array. And as you said, the dimension of the ith matrix will be array of I minus 1 cross array of I. And you have to find the most efficient way to multiply the matrices together such that your total number of element multiplication will be minimum. So the naive approach, what is the naive approach that comes to the first approach that comes to your mind will be you just place the parentheses at every possible place. Like for ABCD, this can be the possible thing. So yeah, the split you can do, or the 3 cuts that are possible, you can place the cut at after A, after B, or after C. And then you can just find f of ABCD will be the minimum of all these 3 multiplication. The one which gives the minimum will be the answer. In a similar way, the range IJ can be broken, right? The range IJ, you can break the similar range IJ in the form of I to I plus 1. And the another part of the matrix will be I plus 1 to J. So here what we do actually, if you have a series of matrices, you divide it into the 2 groups, and then you find what will be the cost of multiplication of this matrix with the resultant of their multiplication. In the same way, this can be the one possible case. The another possible case will be I to I plus 2 from I plus 2 to J, and so on. It will be I to J minus 1 from J minus 1 to J. So you can, this range can be broken it into 2 groups, and then these groups can just take the first yellow color group. This group can be further divided into the smaller groups until you get only 2 matrices, or the one matrix which whose cost of multiplication will be 0. And then you will just combine all these solutions and will find what will be the minimum number of multiplication, and that will give you the answer. So now if you need to solve it in the recursion way, how we will solve that? Let's see. Wait, I guess the split is cleared, right? It's, yeah. So what you will do, you have been given the sequence of the matrices, so you'll separate it into the two subsequence. You'll find the minimum cost of multiplying out each subsequence. You will add their cost and add in the cost of multiplying the two result matrices, and then you will do all for all the possible position at which this subsequence can be done. So let's see how we will do that. Okay, so let's just again take this example ABCD, where again you have been given a 4-sized array. As you need to find the minimum cost of multiplication of these 4 matrices, you begin with finding all the possible solution. And then you begin first of all splitting those, and then you split it at A, B, and C, D, and then you split it at C and D. So here actually if you see you are splitting and the same splitting goes in the array. So for that taking care of the split, we will introduce one new parameter, that is K, integer K, that will start from, let's say, I. If you haven't given a size array I to j, you will start splitting from I till before j minus 1. And then for all possible splits, you will calculate what is the cost of multiplication. And among that split, you will find which is the minimum. And that will be the answer. So for that, we will start with we will call the start with the function, which will take one as two integers, let's say I, j, and the array that stores the dimension of the matrices. Then we will go with the, so first as you need to do, first of all, it starts with your base case that if I is equals to j, you will return 0. See, when I is equals to j, it means you have been only one array index. That means you have only one matrix, that is, let's say A or B or C, D. So their cost of multiplication will be 0. So you will return 0. If I is not equals to j, then you will run a for loop. The for loop that will take care of the splits. So if, as you know, if this was the array, we can say that ABCD, to just give the dimensions of ABCD, we always start with this index I. So index dimension of array matrix A will be array of I and array of I minus 1. And whenever we pass to this, we will always pass this array of ith index, not the previous index, because we can just take care of that index. So whenever you need to pass, you will pass to that function 1, comma, n minus 1, and the array, let's say P. And then later, when you write the for loop, your splitting will start from k equals to I, and it will go less than j and the k plus plus. When you go for the splitting, first of all, the thing is that when you find, let's say you are saying what will be the cost of multiplication for multiplying I till j, that multiplication will be multiplying of p I k plus multiplication of p k plus 1j and the cost of multiplication of these two matrices. That will be p into I minus 1 into p of k into p of j. So if you see that by an example, if A, B, C, D was the matrices, and if you have been given this 0, 1, 2, 3, and 4, in that case, your I was 1, your J will be 4, and you start splitting from K. So first of all, you call the multiplication of M, P, the array. The I is, let's say, 1, and the K here, the split is 1. So the cost of multiplication of this at the first will be 0. And this will call m of p, k plus 1 will be here 2, and j will be 4. You need to calculate this. So in the same case, if you split from a, b, c, d, first you need to calculate the multiplication of a will be, of course, 0. You will find the multiplication of cost what is bcd, which will be given by the next thing. Yeah, which will be given by m of p, k plus 1j. And after that, you need to multiply A, B, C, D. That cost will be given by P of I minus 1 into P of K into P of J. So, okay, can someone tell why it is I minus 1 instead of I? Is it right? Anyone? Or is the naive approach clear to everyone? Does anyone have any doubt? I guess no. So the thing is that when you split any array from the index I to index j, say you split it at k. So what we say, anything m of I, j, p will return you the minimum cost of multiplying the matrices ai, ai till aj. So now if I'm splitting it at k, it means I have two bunch of matrices. One is from ai to ak, and another is a of k plus 1 to k of j. So I need to find the minimum, or I need to find the cost of multiplication of these matrices. So first of all, I'll call the function on this set of matrix that is from I to k. So I'll call the function that is p of, let's say if the function is m of p is the array index I and k, that will give me the cost of multiplication of the matrix from I to k plus the cost of multiplication of the matrix a plus 1 to j. And after this, you need to also add the cost of multiplication of the resultant of these two matrices, which will give you the total. So here, as you know, we are passing the ith index, and the dimension of the AI matrix will be array of I minus 1 and array of I. And we know the multiplication of these two will result in the matrix of dimension array of I minus 1 cross array of k. In a similar way, the matrix multiplication of this one will result in the matrix of the dimension array of k cross array of j. So if you need to multiply these two matrices, their cost will be array of I minus 1 cross array of k into array of j. And that's how you will get the total cost required for their multiplication. I guess that's clear. So just let's see. Yeah, so this is the code for the recursion, for the naive approach. So here, the first of all, it starts with, okay, the matrix chain ij will return what will the minimum cost for multiplying the matrices from ai to aj. P will be the array which stores the dimensions of the matrix. And for calling this, you will call with array and not here. You should notice that it should not be 0, it should be 1 as discussed earlier, and n minus 1 where arrays of size n is used. So the base case is start if the both the index are equal, it means you have only one matrix, and of course its cost of multiplication will be 0. So return 0. Uh, then you use the int many as you are storing it as int max because you will use it to store the minimum cost. And so first of all, now this is how the splitting works, or you can say how you are placing the parenthesis, or how you are splitting the matrices between the first and the last matrix. Then you calculate for any split, you calculate what is the cost of the multiplication for that split and compare if it is minimum than the before. If it is minimum, you will change the mini, else it won't change. In same way, it will go for on and you will return the minimum count, which will be the minimum cost of multiplication. Okay. So as you know here, the time complexity is exponential, but the space complexity is of course constant because you are not using anything to store here. And you know that what is the reason of this exponential time complexity is the recursion. And as the size of the matrix or as the size of the array increases, the number of matrices will be more, and the recursion will go down deeper and deeper, and some sub problems that are repeating will be repeated. As a result, increasing the cost of computation, and hence you get the time complexity as exponential because it does a lot of redundant work. So yeah, the question is that was a naive approach. Now let's go if the dynamic programming works here or not. So does anyone wanna suggest how it works here? Or let's start with why dynamic programming works here, or like what are the properties that the question should follow for the dynamic programming to work. As you know, there are two properties. The one is optimal substructure and another is the overlapping subproblem. So what is optimal substructure? If you look at optimal substructure, it is actually the thing that you have the bigger problem can be divided into the smaller subproblem, and the computing the answers of the smaller subproblem will give you the result or will give you the solution to the bigger subproblem. Yeah, so yeah, does it follow optimal substructure property? Yes, it does, because you are following a recursion. As you can see here, this is a recursion where you're calling the function again itself, and it is calling. So if there is a recursion, it means it's breaking the smaller problem. Sorry, the bigger problem is breaking into the smaller problem. You're calling the function again, and hence the result, it has the optimal substructure property. The second property that the problem should follow for the dynamic programming to work is the overlapping subproblem. So yes, it does overlapping subproblem. Let's say if you are computing the cost of multiplication for ABCD, it can be, as we told, it can be split in three, either A into the BCD, AB and CD, and ABCD. The first can other again be split into two, A then multiplied with B and CD and ABCD. So if you see here, yes, CD, the sub problem is being repeated, and this is one of the sub problem that is repeated here. It means that it does have the overlapping sub problem too, though the number of the matrices are less, therefore the number of overlapping sub problems will be small. But as the number of or the size of the array increases, this too shall increase and result in a heavy time complexity. So yeah, you can see that f of CD computation is repeated. So you can say it's possesses the property of overlapping subproblems. So now you can say that as it has both the optimal substructure property and overlapping subproblem property, the dynamic programming will work here, and you can calculate the answer to this problem by either you will construct a temporary array, either you can compute it in a bottom-up manner or in a top-down approach. So yeah, that's all. So yeah, first of all, you are using the top-down approach or memorization. as you know, what you do in top-down approaches, you start from the bigger sub-problem, you break it into the smaller problems, you calculate their answer, and then you get the resultant. In the same way, we will also use a matrix DP for the memorization purpose. Or okay, so like, does anyone wanna suggest how can we use the DP here? Or how can you solve it with the help of top-down approach? Okay, so let's say you are that is actually, if you see, it is way too much resemblance to the recursion that we had done earlier. But the only thing, the recursion that we were following here was that there were some sub problems which were repeated again and again, and their computation was causing a lot of work that could be reduced. So for that, we need to just create a table that will store the values. So if you see here, what you need to do, these things will remain the same. The only thing you need to is that, first of all, the whole DP table or the 2D matrix that you will be using should be initialized with the -1. And it means that the value has not been computed till now once even. And after that, you will be using DP of, if you find DP of ij to be -1, let's just say this. Yeah. So for writing the top-down approach or the memorization, what you need to do, you need to begin with, first of all, the base case that will be. So first of all, while writing, you will first of all let's first of all write what will be the state. If let's say your DP of ij is the state, so DP of ij represent what will be the minimum cost of multiplication for matrices ai till aj, and this is what will be your state will be, and the next will be the transition. The transition, as we have discussed already in the recursion, the transition will be the same. Your DP of ij will actually be the minimum of DP of ij, comma, the following split, if it will be when you are running a DP of I, with that will be, if you will call the matrix multiplication, that will be the function MCM P I of K plus MCM P K plus 1 J plus P of I minus 1 into P of K into P of J. So this will be the transition, as DP of ij will be the already computed one, and now the split that you will be doing, which that this will remain the same. So if you see, the changes that needed to be done between here is the only the table that you need to introduce here, and you should search first if your DP of ij is equals to -1 or not. Yeah, so if your DP of ij is not equal to -1, it means that the value has been computed and you will return the DP of ij. if the dp of ij equals to -1, it means that the value hasn't been computed yet, and you should assign it a maximum value because you will be using the minimum function here to find the minimum. And then you will split the function, the split function that you will be using here will the split, and will find which is the minimum among them, and you will return the minimum, that will be dp of ij, that will return the minimum cost. And the matrix chain memoized will be, you will be calling the function with the 1 index and then -1. So if like the recursion is, or the naive approach is clear, then you can just see that the only difference here has been introduced is for using a 2-dimensional array, and the rest all is the same. So the use of the 2-dimensional array helps in memorizing that, which decreases the time complexity from exponential to the n cube. Uh, is the top-down approach clear? Does anyone have any doubt? Okay, so yeah. Let's go to the next approach, or the tabulation or the bottom-up approach. So as discussed earlier, the tabulation or the bottom-up approach is starting from the base and then solving the smaller sub-problems, and then using that smaller sub-problems to compute the answer to the bigger sub-problem. So here you need to start, unlike the top-down approach, the bottom-up approach does not have the recursion in it. Either it is called as the iterative approach because you start from the base. So here, what you have to do, you have to start start from the base to move the answer. So here, okay, let's just once see with the help of an example. So here actually let's say this is the 2-dimensional array. Okay, we will only consider the right side of the diagonal. The left side of the diagonal won't be filled. It will always remain to be the -1. So first of all, the first way to fill the matrix is that, as you know, if your I and J are equal, it means the matrix is the only one matrix. So you can see here, this dp of, or you can say 1, 1 implies that the cost of multiplication of a matrix 1 will be 0. So all the diagonal, first you start initializing with all the diagonal entries are filled 0. Then what we do, as we need to start from the base, we start finding what will be the cost of multiplication of all the two matrices, of all matrices of size 2. So or you can say of length 2, you take two matrices and find their cost of multiplication. So here we are first of all finding, if you see here, you will be seeing the cost of multiplication of a matrix 1 and 2 is 120. Then here you find the cost of multiplication of the matrix 2 and 3. Similarly, 3 and 4 and 4 and 5. The same way now because like if you have 1, 2, 3, 4, 5. So what is the multiplication you can do is you can take either 1, 2, you can take 2, 3, you can take 3, 4, and you can take 4, 5. So this is how the table is filled in the first step, in which the length was 2. Then you go to the length 3. It means you can take 1, 2, 3. You can take 2, 3, 4, and you can take either 3, 4, 5. So if you need to calculate 1, 2, 3, 1, 2, 3 multiplication, sorry, 1, 2, 3 multiplication is 1, 2 multiplied with 3 or 1 multiplied with 2, 3. So if you look at the first column, first row, third column, it says that you are multiplying 1, 2 with it says it takes the answer from 1 to 3, and it will give you the answer of what will be the minimum cost of the multiplication if you need to multiply all these three matrices with in the same way 1, 3, 2, 0 and 1, 1, 4, 0 will give you it will give all the cost of multiplication of multiplying three matrices. In the same way, then you go for the 4 matrix, and the resultant is the fifth. So here you can see that the minimum cost of multiplying all these 5 matrices will be stored in the topmost right corner, that will be the dp of 1 n minus 1. So if you see here how we start with starting from the length of the matrix to be 1, and then we proceed till n minus 1 length. In the same way, here what we will do, first of all, if you want to define the state, here it will be the minimum number of multiplications to compute array of I into all these matrices. And so for that, you will start iterating from the length of the matrix. If you start with 2, the length till n minus 1, then you iterate from I equals to 1 to n minus 1, and then you need to find the jth value. Like, because you have found what is the length, then you need to start that what will be the first, the starting point of the matrix, and j will determine what will be the ending point of the matrix. In this way, if you are defining from length equals to 2 to n minus 1, let's say I have A, B, C, D, E as a matrices to be multiplied. So if I define the length as 2, then I need to define what will be the I and what will be the GLI. What will should be the starting index of the matrix and what should be the ending index of the matrix. So I always start with I is equals to 1, which will be this, and I'll go till j. So j will be, as you know, that j can be calculated as I plus L minus 1. So if your length is 2, the j will be B. So you will get AB. Then you will go to iterate. Then you will go to BC and then CD and DE. Similarly, if your length is 3, again you will start from index I equals to 1, and then you can go from ABC, then you can go to BCD, and you can go to CDE. Yeah. So the code for this problem will be, you are being given an array and integer n will be the size of that array. So you initialize a 2-dimensional array of n cross n, and you have, so first of all, what you do is all the diagonal elements of that matrix are initialized to be 0. Then in this for loop, what you do, you start taking the length of the array, because you have to start from the base. That will be it starts with the length of a matrices of 2, and it will go till length less than n. Then you start in the second inner loop, you decide what will be the starting index of the matrix to be multiplied, and j will determine what will be the ending index of the matrix. That will be calculated with this I plus L minus 1. And then you initialize your dp of ij to be the int max, the maximum value. And again, the same transition that you have seen, the dp of ij will be the minimum of the one that has been calculated. And then you will return the dp of 1, or the n minus 1 which will return the minimum cost of multiplication. And there are 3 nested loops, and 1, 2, 3, and these all will be executed at most n times. Here this will be executed n times, the same n, and here also it will be executed for the n times. So we say that again this also has the same time complexity as compared to the top-down approach, and even the same space complexity. The only difference is that the top-down approach uses recursion and the bottom-up approach doesn't use the recursion. Yeah. So that's all. Does anyone have any doubt regarding anything? Or any point that isn't clear, you can raise now. Okay, so that's all for the session. Thanks for joining the session. And the recording and the slides will be posted. Of course, even the problem set will also be posted. Okay, so thanks a lot for joining the session. And yeah, if anyone has any doubt, they can ask, or any part that is not cleared.